Okay, students, welcome to video class number 26. And this is frequency domain analysis of a second order system. So, hope you have remembering that in our previous video we have studied about time domain analysis. And from time domain analysis, we have seen some time domain specifications uh, like peak, rise time, peak time, and then maximum overshoot, settling time. All these are time domain specifications. So similarly, we have so using this we can explain some of the characteristics of the system. That's why we studied the time domain analysis. Similarly, if you perform frequency domain analysis also, we'll be able to study some other characteristics which we may not be getting from a time domain approach. So they're also similar to these specifications. There also we'll be studying some of the frequency domain specifications as we go deeper into this course. Okay, deeper into this topic. Okay, so before going into the frequency domain analysis, let me tell you the definition of frequency response. Okay, so I'll be starting with the general case, and later we'll be applying this to a second order system. So for that, consider a system with the with the with the with the impulse response as m of t with input r of t and c of t. Now assume that the system is a stable LTI system. You know what is an LTI system, which we have studied in signals and system course. Now, now the meaning of frequency response is when you give the input a sinusoidal input, say something like this. When you give a sinusoidal input, so this is the sinusoidal input that we give here, you are going to get again a sinusoidal signal, say maybe of this form. Okay, maybe, okay, this is a sinusoidal signal. So maybe you may be getting a signal like this. But what you can notice is, if it is a linear system, what you can notice is the time period is the same in both the cases. The difference is, so time period same means frequency will be 1 by t, so you'll be having the same frequency. So for a linear time invariant system, when you give a sinusoidal input, this is also a method by which you can check whether a system is linear. So we have already studied the superposition principle. Now if a system is said to be linear, it has to give a sinusoidal output for a sinusoidal input with the same frequency. But what is the difference? Now when you analyze, this is just an example. Now looking at this example, you can see that its magnitude changed, right? So one of the thing that changes magnitude. So this change depends on the characteristics of the system, right? So that is the implication of this frequency response, and that's why we perform frequency domain analysis. So similarly, when you look at this example, another difference is with regard to its phase, right? Now this you can, so this response, so from this response you can find out the magnitude as well as phase, and as we go further we will understand this magnitude depends on the frequency omega, phase also depends on frequency. That means what I want to say is, if you suppose if you give frequency as the same signal with the same amplitude but the different frequency, you won't be getting this. I mean, sometimes you may be getting something like this. Okay, a wave, something like this. That means here also magnitude varies, phase varies. So from this you can see that the magnitude as well as the phase varies according to frequency. So combining this magnitude, so you can call this as the magnitude response. This is the response, magnitude of the response, and there's a phase. So we'll be representing that by 1 by m, another by phi, and this is m of omega, this is phi of omega. So this response, this frequency response can be of can be divided into two, that is the magnitude response and the frequency response. Okay, now coming to a bit more generalized, I'm going to generalize this again. Say if you have a, since it is a linear system, that should obey or this equation is valid, right? R of t star m of t, right? So that is the impulse response star the input. Now in the frequency, in the S domain, you can convert this equation as R of S into M of S. This is by applying convolution property. This is by convolution property, right? Now using this, you will be able to get this R of S. Now what is this R of T? Now in order to get the frequency response, we have seen that the input has to be sinusoidal. For that, I'm assuming the R of T has to be A sine omega t. You know what it is. It is a sinusoidal input, okay, a sinusoidal input with a maximum amplitude A, right? And this omega is 2 pi f, or f is nothing but it is the inverse of this time period. Okay, so this is the input that I'm going to give. Now as I told you, since it's a linear system, you will be getting exactly a sinusoidal output with the same frequency, but they will be differing. The magnitude will no longer be A, and there will be an additional phase along with this. Omega t will plus some phi of omega will be the output. So this is what we are going to analyze, how this magnitude and the phase varies according to the change in the frequency, and we keep on changing the frequency. This is how you find out the frequency response of an amplifier and so on, right? You set an input, you keep on changing the frequency. At each frequency you will be considering the output, and from that output you will try to draw the magnitude plot. Okay, so that is frequency response. Now using this equation, you can write the C of S to be, C of S is equal to, what is this R of S, or you can write in this way, say M of S into R of S. I'm rewriting it for you. Now this transfer function can be considered as a numerator to a denominator polynomial, right? This is a transfer function. This is of the form P of S to Q of S. I'm just using this N of S by T of S into R of S. Now what is this R of S if R of T is A sin omega T? This R of S will be equal to omega by S square plus omega square, or this can be written as omega by S plus j omega into S minus j omega, right? So now so that means you can replace this by omega by S plus j omega into S minus j omega. Okay, so there is a slight correction. So there is an amplitude, you need to consider that. So you need to multiply this by A. So this will be A omega by S plus j omega into S minus j omega. Now when you factorize this d of S to 0, that is the denominator polynomial of this transfer function, you will be getting some poles, right? P1, P2, P3 and so on. So that means this is going to be say all these are negative values. I mean, since it is assumed, another assumption is to be made for the system is a stable system. Okay, we are just studying about a stable system. Now what must be the speciality of the poles of a stable system? That should lie on the left half of the S plane, meaning the real all the poles should have a real term less than 0, or it has to be negative. So since this is negative, you can say you can call this N of S as or this M of S can be written as by S plus P1, right? S plus P1, because it is S minus, the factors are usually S minus P1, but we know that P1 and P2 all are negative, so you can write this as S plus P1 into S plus P2, etc. up to S plus Pn. And what is this N? N is actually the order of this polynomial, and assume that this is an nth order polynomial, In that case, you will be having this much roots. This into a into omega by s plus j omega into s minus j omega. Okay, so clear. Now what next? You can convert this into resolve this into partial fraction. Now resolving this into partial fraction, you will be getting this as, say, I'm using the constant k1 by s plus p1 plus k2 by s plus p2, okay, plus etc. up to kn by s plus pn, then plus next is plus okay, I'm calling this coefficient as a1 divided by s minus j omega plus a2, or it is a1 star by s plus j omega. I will explain why it is. So you might have studied in your lower classes that if the poles are complex in nature, then how to find a complex poles means complex poles always occurs in place pairs. So that means if you have s minus j omega, you must have s plus j omega. So it is enough to find out the coefficient of a1. The other coefficient will be the conjugate of this. Okay. So anyway, we understood that this a1 and this a1 star is of the form a plus jb. That means it will be of a complex, even though these are coefficient, there will be a complex coefficient because of the impact of this complex poles. Okay, now what next? Next is to find out the inverse of this. So while finding the inverse, you will be getting the roots as k1 into e raised to minus p1t plus k2 into e raised to minus p2t, etc. up to kn e raised to minus pnt, okay, plus a1 into e raised to j omega t plus a1 star into e raised to minus j omega t. Okay, now let's see. I'm going to do, see what happens that I'm going to increase this t. Now as t varies from 0 to infinity, right? Definitely this has to vary as from t. So as t tends to infinity, we have seen that the c of t approaches its steady state, right? So this will be having this particular signal, this particular system will also be having a transient state and a steady state. Now, or in another sense, if t becomes much higher, what happens to these exponential signal? Since the powers are negative, as t increases, all these exponential part reduces to almost becomes equal to 0. Now, even at a very higher times also, there will be a value for e raised to j omega t, because this can be converted. This is e raised to j omega t and e raised to minus j omega t. So this can be converted easily into cos omega t or sin omega t. So for any values of time, there will be a value for cos and sin that won't reduce to 0. But because of the exponentially decaying nature of this part, that is this first part and this second, this is the second part called this first part will reduce to 0, or you can neglect that. So finally, the steady state output will be equal to a1 e raised to j omega t plus a1 star e raised to minus j omega t. Now the question is, what is this? How to find out this a1? So you have studied already in the partial resolution. I'm not going to in the details of that. So a1 will be equal to the so from no, this is equal to c of s, or this particular signal is equal to m of s into r of s, right? Now what is this r of s? So what you do is you will be multiplying by the whole factors throughout. That's how you will be doing, and putting s is equal to j omega. All these factors gets reduced to 0. The only thing that remains here is a1, right? Okay, that's how you used to do. So multiplying throughout and eliminating all this. So during that process, when you put s is equal to j omega, you will be getting this as, this is nothing but this is m of s into a omega by, okay, A omega by S plus j omega at S is equal to j omega. This is how you need to find out. So you may just use the just find out the coefficient as you did in the while you resolve the partial fraction. You will be able to arrive at this, calling this m of s. So using this expression, so this can be written as the same thing is equated as m of s is into r of s. That can be equated as this. So when you multiply with all this with the coefficients, you will be getting this as a1 into, okay, a1 into like this, m of s into a omega by s plus j omega at s is equal to j omega. So you may find out by yourself, so that you will be getting this as m of j omega by j2. Okay, now this m of j omega, that is at s is equal to j omega, this m of j omega is actually the transfer function of that system. Now this transfer function, this is of the form a plus jb. Now if m of j omega is of the form a plus jb, you can write this quantity as the magnitude of j omega and angle, or you can write like this, e raised to j phi. Okay, so that you will be getting this as a by j2 into magnitude of m of j omega into e raised to j phi of omega. Meaning, as I told you earlier, what is this? This is actually the, this one is actually the your magnitude. This one is your phase. Look at that. The magnitude depends on frequency. Phase also depends on frequency. So you can have a plot of m of j omega versus omega. This we call as the magnitude response. Okay, this is called as a magnitude response. Similarly, you can have the e raised to j phi of omega versus omega. You will call this as the phase response of the system. Okay, now usually the magnitude response is is expressed in decibels as 20 logarithm to the base 10 m of omega. This is very important. We'll be using in the subsequent module these expressions. Okay, so these from this frequency characteristic, or from these characteristics, we can these characteristics can explain or describe the steady state output of the system. Okay, so in the time domain analysis, that's more prone to so all those specifications are related to the transient response, while this one gives you more idea about the steady state output when you give this input as a sinusoidal input. Okay. Okay, now once you get this a1, it is very easy to get a1 star, right? What is a1 star? It will be put everywhere where j is found a negative sign. So this will be minus a by 2j, right? So this will be m of, since it is magnitude, that won't affect the sign change, while the phase will be changing, right? This will be minus j phi of omega. Now you can use this expression again. Now substituting this in a1 and a star, you can finally arrive at c of t as equal to a into m of omega into sine omega t plus phi of omega. Okay, I'm not going to do the derivation of this. So look at this. This is the response. This is the output response when you give a sinusoidal input. So that results in two aspects of that. Now, when you divide this response, you can see that there is a magnitude part which varies according to frequency. There is a phase part which depends upon the frequency. Look at this. You are having the same frequency as omega as we start here, right? You have inputted a sine wave with the frequency omega. You are having the same frequency. The frequency is unaltered, but magnitude and phase varies as you increase or decrease the frequency. Okay, now the next is the frequency response of a second order system. Okay, so next is the frequency domain response of a system. So far we have just found out the response of a general system. Now we are considering a second order system. So your M of S is, you know what is uh, um, the transfer function C of S by R of S is equal to omega n square by S square plus 2 zeta omega ns plus omega n square. Okay, now how to find out the frequency response? We have already seen that. So in the previous so what you need to do is, say, putting s is equal to j omega. So this is the thread for finding out the sinusoidal response. If from this I'll just give you an idea. So whenever you give a sinusoidal input, you can put s is equal to j omega. You won't be considering the sigma part. We can avoid that sigma part. You just need, because you are worried only about the frequency part, right? J omega. So why you give sine omega? You are not interested in that sigma or anything else. When you give a sinusoidal input, you want to change the frequency, okay, the input frequency, and you want to measure the magnitude as well as the phase of that, as we have seen earlier. Okay, so what you need to do it, so in order to obtain the frequency response, very important response, put s is equal to j omega. So that means you will get this as, this transfer function we call as the sinusoidal transfer function. So okay, hope you understood how to get the sinusoidal transfer function. In a transfer function, put s is equal to j omega, so that this becomes omega n square plus j omega square plus 2 zeta omega n j omega, right, plus j omega plus omega n square, right? Now uh, what can you say about this? So you can have a manipulation on this. You can bring this omega n square down, and separating the imaginary and real term. So this becomes a real term because j square becomes real term. This is also real term. Bring these together and separate this complex part, and bring this omega n square to the downward, so that you will be getting this as 1 by 1 minus omega by omega n the whole square, okay, plus j into 2 zeta omega by omega n, right? Omega by omega n. Now once if you get the sinusoidal transfer function, what is actually, so once if you get m of j omega, we have seen that from this how to get the frequency response. So in order to get the frequency response, what you need to get is the magnitude as well as the angle of m of omega. Now what is the magnitude m of omega will be 1 by root of, okay, 1 by root of 1 minus omega by omega n the whole square, that is a plus jb of, so it will be root of a square plus b square plus 2 zeta omega by omega n the whole square, right? So this is it. Now what will be your phase? Now how will you calculate the phase? Or this can be written as phi of omega. Now what is this phi of omega? If you have a plus jb, it will be tan inverse b by a, right? So applying this, so what is this? A plus 1 by okay, you are going to find out the phase of this. So the phase of this will be, the phase of the numerator will be 0, the denominator will be tan inverse b by a, or it will be minus tan inverse b by a. So that what is b? B is this thing, okay? So this will be tan inverse 2 zeta omega by omega n, right, divided by 1 minus omega square by omega n square. Okay, so this is your phase. Now that means when you, look at this. So this magnitude depends on the frequency. Similarly, the phase also depends on this frequency. Now you can have a plot of this. When you try to plot this, I'll just give you an overview of that. I'm not going to much details. Now, what I'm going to do is say what happens at omega is equal to 0. At omega is equal to 0, this becomes equal to 1, right? This becomes 1, I mean 0. This is also 0. So this will be 1 root of 1, which will be 1. So m of j omega will be equal to 1 at omega is equal to 0. Now what about at omega is equal to infinity? At omega is equal to infinity, this becomes almost equal to 0. So that means if you want to plot this, if you want to plot this, this is actually, this is in the omega, this one is m of omega. So as omega is 0, its value is 1, right? Yes. Then it says that at as omega reaches infinity, that is along this will be, yeah, this will be 0. So you may be feeling that it is going like this. No, there is no exponential term or anything like that. That's not the way it is. So as you can see that this is 1 minus, and as 1 minus, that means this is going to be a very small quantity. Okay, 1 minus this quantity is going to be a very small quantity at the lower frequencies. So since it is lower for some time, this will be increasing. So if you simply substitute some values, say some substitute some omega n as some 5 radians and so on, and simply try to plot this, so you'll be getting a graph something like this. Okay, and this particular function is going to reach at a maximum value, and after that this reduces. Okay, this is how you are going to get the graph. Now, okay, now the max, this magnitude response will be reaching a peak value. This peak value is called as the peak resonance. It is not the frequency, mind it, it is the peak resonance, and the frequency we call as the resonance frequency, the resonance frequency. And I'm going to show you one more thing. So this amplitude reduces up to 0.707, or it is a, okay, this is the 1.707 is called as the, you have studied in your filters, and hope you are remembering that those are called as the half power points. Now this is called as omega c, or we call that as cutoff frequency. Okay, now this cutoff frequency is required to define the bandwidth. So look at the things which you are getting from the frequency response. Now in a time domain approach, we have seen rise time, peak time, settling time, and all those things, while in a frequency response you are getting some other informations. Okay, okay, now coming to this, so this response we call as the magnitude response. Okay, this is the magnitude response. Now coming to the phase, now let us try to plot this. What about this phi of omega at omega is equal to 0? When you substitute omega is equal to 0, this becomes 0. Okay, that phi of omega is equal to 0, right? Now what if omega becomes equal to omega n? At omega is equal to your natural frequency of the system, what happens is this is 1, and what is going to be this? That is omega is equal to 1, meaning this is 0. So your phi of omega is going to be equal to minus 90 degree, right? Now what happens when omega becomes equal to infinity? When omega becomes infinity, this is again, omega is infinity, so this is also infinity. So what you are going to get is phi of omega is going to be equal to minus 180 degree, right? Now you can have this, you can have the omega by omega n. So this is omega by omega, in this case omega by omega n will be equal to 1, omega by omega n is equal to infinity, omega by omega n is 0. So as you try to plot this, you will be getting a graph like this. and if this is, assume that this is minus 90 degree, this is minus 90 degree, this is minus 180 degree, and this one is 0 degree. You can see that the graph starts from the phi of omega. It at omega is equal to 0, this phi of omega is 0. Now as it reaches as omega, this becomes equal to 1. When this becomes equal to 1, this graph touches this 90 degree, and it goes on at minus 180 at infinity. Okay, this is how it looks like. So this is called as the phase response of the system. Now, using this magnitude response and phase response, apart from the things which we have specified here, that is the resonance frequency, peak resonance, cutoff frequency, and if you have cutoff frequency, you will be able to get the bandwidth as well. And apart from this, you will be studying gain margin and phase margin. We'll be dealing that in detail in the next module, so you don't have to worry about that. Anyway, just understand there are some terms like gain margin and phase margin which you actually get from the frequency domain analysis of a system. So hope you understood this class. Okay.